In this section, we discuss the very famous Bayes theorem and statistical independence. As we will see during this and the next lesson, the importance of Bayes' theorem to help computing conditional probability cannot be overestimated, to the point that it has been said that Bayes' theorem is to the theory of probability what the Pythagorean theorem is to geometry. Remarkably, this important theorem can be obtained simply by rearranging the definition of conditional probability, that is, this formula here. The formula was this one, so if we multiply each side by P of f, we obtain this formula here. That is, the probability of the simultaneous occurrence of events E and F is equal to the conditional probability of E given F multiplied by the probability of F. However, since the intersection is symmetric, we have that the probability of E intersection with F is equal to the probability of F intersection with E, and so we can exchange E and F on the right-hand side of this equation, obtaining this. Since these two probabilities are exactly the same, then also this product of probability is exactly the same. The last equality gives this formula, which is usually written in the form presented in Bayes' theorem. Given the events E and F belonging to the sample space S of a random experiment, with a probability of E strictly greater than 0, then this formula holds, which is called Bayes' theorem. Notice that here we have two conditional probabilities, while in this fraction we have unconditional probabilities. Bayes' theorem shows that the conditional probability in general is not symmetric. In fact, we have this factor here, which is 1 if and only if the probability of the event E is equal to the probability of the event F. In that case, we can erase this factor and we have perfect symmetry between the two conditional probabilities. If you are interested, here you can read a little bit of history regarding Bayes' theorem. As always in probability, we have peculiar names for everything, which is also the case for the objects appearing in Bayes' theorem. P of f is called the prior probability of the event F. P of E is called the marginal probability, and it serves as a normalization factor. Look at here. Then we have the conditional probability of E given F, which is called the likelihood. And finally, we have the conditional probability of F given E, which is called the posterior probability of F, given that E occurs. This one is the easiest possible formulation of Bayes' theorem. Before giving a generalization, let's recall what we have seen so far with a short video.
Let's recap in this video both conditional probabilities and Bayes' theorem. First of all, remember that conditional probabilities must be used each time the sample space must be updated because we have gathered novel information. We have seen that given two events E and F with F having non-zero probability, the conditional probability of E given F is written with this symbol here, and it's defined as the fraction between the probability that the two events occur simultaneously divided by the probability of F. We have also seen that conditional probabilities can be highly non-intuitive, and so I strongly suggest you to leave your common sense aside and just use mathematics when you deal with conditional probabilities. Bayes' theorem is easily the most important one related to conditional probability. It says that we can pass from the conditional probability of E given F to the conditional probability of F given E, introducing this factor here given by the fraction between the probability of F and the probability of E. As always, in probability we have a peculiar language, so even in the context of Bayes' theorem we must learn how to call the objects that appear in this theorem. P of F is called the prior probability of the event F, P of E is called the marginal probability, P of E given F is called the likelihood, and P of F given E is called the posterior probability of F given that the event E occurs.
From this theorem here, recall that if we have a partition of the sample space S, then this formula holds. That is, the probability of the event E can be written as the sum of the probabilities of E intersected with all the events of the partition. This formula is often called law of total probability. And since for all event F we have that F and its complementary set form a partition of S, we have that the law of total probability can be written in terms of this partition like this. We're going to see that the law of total probability will allow us to prove the generalization of Bayes' theorem. Writing again like this a partition of S, we have that Bayes' theorem can be written as follows. If this expression seems complicated to you, let's consider the easiest possible partition, this one. Then we have that the generalization of Bayes' theorem is given by this formula here. If we compare it with the original version of Bayes' theorem, we see that the whole difference is in the denominator. Let's now examine the proof in order to understand why the denominator in Bayes' formula can take these expressions. The first step of the proof consists in applying Bayes' theorem to each event of the partition, like this. But thanks to the law of total probability that we have just recalled, we have that the marginal probability P of E can be written in this form here. Now we rewrite this using the very definition of conditional probability. From this formula, we find the possibility to rewrite this probability in this way. So, in the law of total probability, instead of using this probability of intersection, we can use this product of probabilities. This gives us the possibility to rewrite the law of total probability like this. The last step consists in replacing the probability of E with this probability here. What we obtain is precisely the generalization of Bayes' theorem. We're going to use immediately the generalized Bayes' theorem to provide a much simpler solution to the three prisoners problem that we have discussed in the previous lesson. Before continuing the video, it is strongly recommended that you carefully review this problem in your notes or revisit the video from lesson 3. So, if you have revisited the example, you know that we have indicated with A, B, and C the events that the prisoners A, B, and C, respectively, will be pardoned, and with W, the event that the warden tells A that prisoner B remains in jail. The probabilities A, B, and C are identical, and their value is 1/3. Now consider the fact that the sample space of the three prisoners problem is this one here. One prisoner will be pardoned, and two will remain in jail. It turns out that the events A, B, and C form a partition for this sample space. In fact, it is clear that they reconstructed with their union, and moreover, they are disjoint, because only one prisoner is pardoned. We can use this important information to write the generalized Bayes theorem in order to compute the posterior probability of A and C being pardoned given the event W. That is, the warden tells A that the prisoner B remains in jail. Recall that the generalized Bayes theorem is given by this formula, and if you replace E with W and the partition Fj with A, B, and C, you can write these formulas. Now notice that all the probabilities that I have highlighted are known and their value is 1/3. So the only unknowns that we have to compute are these ones. Let's start analyzing the first conditional probability. If A occurs, it means that the prisoner A will be pardoned. Then the warden can tell A that either B or C will remain in jail. This means that this conditional probability is 1/2. Now let's analyze the second conditional probability. By definition of the event B, it occurs when the prisoner B will be pardoned. So the warden cannot tell A that B will remain in jail because this is not true. Hence, the event W cannot occur. Otherwise said, the event B and W are incompatible, and so this conditional probability is 0. Finally, let's analyze the third conditional probability. By definition of the event C, it occurs when the prisoner C will be pardoned. But if you remember the analysis of the three prisoners problem that we have conducted in the previous lesson, this is exactly the case in which the behavior of the warden is deterministic, that is, the conditional probability is 1. Finally, if we introduce the values that we have just computed in the expression of these conditional probabilities, we find the correct solutions to the problem, but faster and easier with respect to the analysis conducted in the previous example. The three prisoners problem is mathematically equivalent to another very famous and apparent paradox called the Monty Hall problem. Let's read it together. Suppose you are on a game show and you are given the choice of 3 doors. Behind one door is a car, behind the others, goats. You pick a door and the host, who knows what's behind the doors, open another door which has a goat. Then he asks, do you want to switch your initial choice? The problem is, probabilistically speaking, it is to your advantage to switch your choice or not. We're going to analyze this problem in 2 ways. The first without mathematics, and the second with the Bayes theorem. First of all, suppose that you don't change your initial choice. Then there is only one possibility to win the car, that is, when it is exactly behind the door that you chose. But there are 3 doors, hence the probability of winning is 1/3. Now instead suppose that you change your initial choice. And to fix the ideas, let's also suppose that the car is behind door 1. There are 3 cases to analyze. First, you chose door 1. Then, independently of the door that the host opens, if you switch the door, you lose. The second case is when you chose door 2. Then the host is bound to open door 3, revealing the goat. The only switch you can make is to door 1, and you win the car. In the third and final case, you chose door 3, the host is bound to open door 2, revealing the goat. You can only switch to door 1, and you win again the car. So, if you remain stuck with your initial choice, you have probability 1/3 to win the car. Instead, if you modify your initial choice, you have 2 possibilities over 3 to win the car, that is a probability of 2/3. We are now going to see that if we use the Bayes theorem, we get exactly the same result. To fix the ideas, suppose that we have chosen door 1 and that Monty opened door 3, revealing the goat, as depicted here. If we want to apply Bayes' theorem, we need 2 events. The first one is the event C, which is the car is behind door 1, and the second event is M, that is, Monty has revealed a goat behind a door different than 1. The simplest version of the generalized Bayes theorem, that is, this equation here, says that the posterior probability that the car is behind door 1 given that Monty opens door 3 revealing the goat is given by this formula, where of course the complementary of the event C is the event a goat is behind door 1. In the next page we analyze all the objects appearing in this formula. P of C is the prior probability that the car is behind door 1, and we have already seen that its value is 1/3. The meaning of this probability is the following. Given C, there is a car behind door 1, Monty opens a door different than 1 with a goat behind it. However, Monty always shows a goat, so this probability is 1. The meaning of this probability is the following. Given C complementary, there is a goat behind door 1, Monty opens a door different than 1, showing a goat. But again, Monty always shows a goat, hence, also in this case, the probability is 1. Finally, this one is the prior probability that we didn't pick the door with the car behind it. We can compute this probability using the fact that P of C plus P of C complementary is 1. So we get that P of C complementary is 2/3. Introducing the values that we have just computed into Bayes' formula, we obtain that the probability of C given M is 1/3. So we see that the probability that the car is behind door 1 is completely unchanged by the evidence shown by Monty. If we consider the three prisoners problem, this is precisely the analog of the fact that the probability to be pardoned by prisoner 1 remains exactly the same after the warden speaks. Now, what about the probability that the car is behind door 2? Well, we can compute it using the following very easy argument. This probability is an unknown, and so we denote it with x. We already know that we have probability 1/3 that the car is behind door 1, while there is 0 probability that the car is behind door 3, because Monty opened this door and revealed the goat. Since these probabilities must sum up to 1, we have 1/3 plus x plus 0 equals 1. That is, x equals 2/3. Which confirms that switching the door gives twice the probability to find the car. However, and this is very important, a higher probability doesn't mean that we will surely win the car, okay? In this section, we introduce the very important concept of statistical independence. We have seen that in the three prisoners and in the Monty Hall problems, in some cases, the occurrence of a particular event has no effect on the probability of another event. The fact that the warden tells prisoner 1 that either one or the other prisoner will remain in jail does not modify his chances of being pardoned. In the same way, the fact that Monty opens a door revealing a goat has no influence on the probability of winning the car if we remain with our initial choice. Mathematically speaking, the probability of occurrence of an event E is not affected by the occurrence of an event F if the following equation holds. A quite natural question that we can ask ourselves at this point is the following. If F has no impact on E, the occurrence of E has or has not an impact on the probability of occurrence of F? To answer this question, let's introduce this equation in Bayes' theorem. We must replace this probability by P of E, but if we do that, we see that we can cancel these factors and we remain with P of F. So we see that the answer to our question is the fact that the lack of influence is symmetric. That is, F doesn't affect E if and only if E doesn't affect F. Instead of expressing this fact with two equations, we can find just one single formula that captures the independence between events. We arrive to that formula using the definition of conditional probability. We can rearrange the conditional probability like this, and if the events E and F don't influence each other, that is, this formula holds, then we can rewrite this like this equation here. This is precisely the formula that captures the statistical independence between events E and F. There's no better way to show the usefulness of statistical independence then discussing how it intervenes in the solution of the problem that started probability. At the beginning of this course, we said that Chevalier de Méré started involuntarily the theory of probability due to his gambling problems. In particular, he was interested in the probability of the event that he could throw at least one 6 in 4 rolls of a die. Let's see how to solve this problem using statistical independence. The probability that we are searching for is equal to 1 minus the probability of the complementary event, that is, no 6 in 4 rolls. But the rolls of a die are independent events, and so we can rewrite this probability as the product of 4 probabilities of not obtaining a 6 in just one roll of a die. Where, as you can see, I introduced this symbol here, which is the analogous of this, but for products. Now, in any roll, the probability of not throwing a 6 is, of course, 5 divided by 6. Hence, we can rewrite this probability as 5 divided by 6 multiplied by itself 4 times, that is, elevated to the power 4. By performing the computation, we obtain around 0.52, which means that there is around 52% chance to throw at least one 6 with 4 rolls of a die. And this is the answer to the question that started the theory of probability. So you can appreciate how easily this answer has been obtained thanks to the mathematical formalization of probability. Let's now discuss the independence of more than 2 events. Let's start with 3 events E, F, and G. We might think that their independence is governed by this equation here. However, we're going to see in the next example that this equation is too weak. We consider the random experiment of tossing 2 dice, and the sample space will be given by the 36 ordered pairs formed by the numbers from 1 to 6, this one here. Then we consider the following 3 events, E, F, and G, where E is the event that doubles appear, that is this one. F is the event that the sum of the 2 dice is between 7 and 10, and the event G is the fact that the sum of the 2 dice is 2 or 7 or 8. You are strongly encouraged to check that there are exactly 6 outcomes for the event E, 12 for the event F, and 18 for the event G. So, using this equation, we can compute the probabilities of these events, obtaining 1 divided by 6, 1/3, and a half. Now we want to check if the probabilities associated to these events satisfy this equation here. The product of the event probabilities is straightforward. So what we have to do is compute the intersection of E, F, and G, and then to compute the probability of the set. It turns out that the simultaneous occurrence of these events can happen only when the sum of the 2 dice is 8 with 2 4. In fact, the sum obtained from the occurrences in event E is always an even number. So we cannot have an intersection between F, G, and E when we consider 7 here and here. Moreover, we cannot have the intersection between F and G if the sum is either 2 or 10. So the only option left is that we throw 2 4s which sum up to an 8. We are left with the probability of this intersection as 1 possibility over 36. This number agrees precisely with the product of the probabilities of each event. We want to check if this equation implies the pairwise independence. Now, the intersection between the events F and G is the event that we throw 2 dice and their sum equals 7 or 8. As a very useful exercise, you can check that this occurs in 11 ways. So the probability of the intersection between f and g is 11 divided by 36, which, however, is different than the product of the probability of f and the probability of g. This is already enough to say that this condition here doesn't imply the pairwise independence. However, again, as a very useful exercise, you can verify that neither the probability of the intersection between E and F is equal to the product of the probability of E with the probability of F. The take-home message is that this equation is not strong enough to guarantee pairwise independence. Now, an interesting thing to examine is if the independence of all pairs of events implies this formula here. However, in the next example, we're going to see that also this condition fails. Let's consider a case in which the sample space consists of 3 factorial, that is 6 permutations of the letters A, B, and C, along with the 3 triples of each letter. Explicitly, the sample space is this one. Here you see the triples, and here you see all the permutations. So the sample space has cardinality 9, and suppose that each outcome of the sample space has the same probability of occurrence, that is 1 divided by 9. Now let's consider the event EI, defined in this way. The ith place in the triple is occupied by the letter A. This means that we have 3 different events. The first one with A at the beginning of the triple, the second one in the second place of the triple, and the third one at the third place of the triple. Since in each event we have 3 outcomes, the probability of E1, E2, and E3 is the same, and its value is 1/3. Moreover, notice that the pairwise intersection between these events is simply the triple AAA. These events contain just one outcome, and so their probability is 1 divided by 9. Thus, we find that the probability of the intersection between each couple of events is given by 1 divided by 9, which is precisely the product of 1/3 and 1/3, that is, the product of the probabilities of each separate event. And this is the definition of pairwise independence. Now we repeat the same argument, but using the intersection of all the 3 events. We obtain that this intersection is reduced again to the only outcome given by A repeated 3 times. So the probability of this intersection is 1 divided by 9, which, however, is different than 1 divided by 27, that is the product of the probabilities of each separate event. So the lesson we learn is that pairwise independence doesn't imply this relation here. And in the previous example, we have seen that this relation doesn't imply pairwise independence. This means that we cannot take one relation or the other as a sufficient condition of statistical independence among 3 events, and we must consider both. What if we have 4 events? Well, also in this case, all the equalities between probability of intersections and product of single probabilities must be satisfied in order to consider those 4 events statistically independent. Here I wrote only 3 of such equalities. As a useful exercise, you are invited to write the remaining ones. As you can imagine, the definition of statistical or mutual independence for n events is quite abstract in order to avoid writing all the possible equalities. Precisely, we say that these events are mutually independent if, for any collection of events written like this, with this specification of the indices, we have that the following relationship holds. This expression contains all the possible intersection between events, and here you see the product of the probabilities of the separate events. As an example of statistical independence, we consider the experiment of tossing a coin 3 times. An outcome of this experiment is, for example, HHT, which indicates that we had 2 heads and then tails. You can check that the whole sample space for this experiment is given by this set here. Now let's consider 3 particular events, Hj, with j that goes from 1 to 3. H1 contains all the 3 tosses for which the first one is heads, and similarly for H2 and H3, as you can see. We suppose that the coin is fair, so we must assign probability 1 divided by 8 to each outcome. And since all the events contain 4 outcomes, we find that their probabilities are exactly the same and their value is 1/2. Let's now verify that these events are mutually independent. Thanks to what we have learned before, we have to check mutual independence for this intersection and also for the intersection of each couple. You can check that this intersection is reduced to the only outcome in which we find just heads, and so its probability is 1 divided by 8, which is exactly what we get if we multiply together the probabilities of each separate event. Now, regarding the pairwise independence, we have that this intersection is reduced to these 2 outcomes, and so the probability is 2 divided by 8, that is 1/4, which is the same as multiplying together the probability of H1 and H2. You can check that this is verified also for the other 2 pairs, and so we get that H1, H2, and H3 are mutually independent events. This means that the occurrence of heads in one toss has absolutely no effect on the occurrence of heads in the other tosses. As a curiosity, at the beginning of the 1990 movie by Tom Stoppard, Rosencrantz and Guildenstern Are Dead, Rosencrantz finds a coin and tosses it 92 times, obtaining always heads. After seeing this, Guildenstern concludes that something is really wrong with reality. Now, after studying probability, and in particular this last example, would you guess the same as Guildenstern?
In this short video, I want to underline the very important concept of statistical independence of 2 or more than 2 events. We start, of course, with the easiest scenario given by just 2 events. 2 events are said to be statistically independent if the occurrence of one event doesn't affect the probability of occurrence of the other. We have seen that in order to turn this intuitive definition into a rigorous mathematical one, we must mix together the concept of conditional probability and Bayes' theorem. We have that 2 events E and F are statistically independent if the probability associated to their intersection is the product of their probabilities. Intuitively, we may think that when we have more than 2 events, then their statistical independence is just the statistical independence of each couple. However, we have seen with counterexamples that this is not the case. When we have more than 2 events, their statistical independence is subjected to a stronger condition, which means that for every subcollection of events, this formula here must be satisfied. Pay attention to the fact that we are not saying that if there exists a subcollection of events such that this formula holds, then the events are statistically independent. We are saying that for every subcollection of events, this formula must hold.
We end this chapter by answering to a natural question. Does the independence of events E and F imply the independence of their complementary sets? We're going to see that the answer is positive. Let's formalize this with the following theorem. Consider two independent events E and F, then also the following pair of events are independent. E and the complementary of F, the complementary of E and F, the complementary of E and the complementary of F. To prove the first property, we must show that this relationship holds. In order to do that, this formula contained in this theorem here comes in handy. In fact, if we introduce in this formula the information that E and F are independent, we can rewrite this term here like this. Then, as you can see, we can factor out the probability of E times 1 minus the probability of F. But 1 minus the probability of F is precisely the probability of the complementary of F. Finally, what we obtain is exactly the formula that we need to prove in order to show the statistical independence of E and the complementary of F. If we interchange the role of E and F, property 1 implies immediately property 2. Instead, in order to prove property 3, we must show that the probability of the intersection of the complementary of E and the complementary of F is equal to the product of the probabilities. But this is equal to 1 minus the probability of E, and this is equal to 1 minus the probability of F. Performing the product, we arrive to this expression here. Now we can use again this formula here belonging to this theorem, but instead of considering E, we consider the complementary of E. So we write this formula. Now, from property 2, we have to recall that the events complementary of E and F are independent, and so this term can be written like this. To conclude, we simply have to notice that this is 1 minus the probability of E, and then perform the computations. You can check that we obtain this expression, which is precisely what we aimed at obtaining. I leave you with some food for thought. Think about the independence of an event E and its complementary.